guys. So let me just show you, you have this paper printed for you, but in case you lose it, I can get you another copy. I can print it for you. But if you want a digital copy, you can go to Canvas. And let's see, main page of Canvas looks something like this. And go over here to course overview, click. And then once it loads, you'll have the material overview. So we're in Unit 3 right now. And the only thing I would probably add to this document for next year is I would just put the percentages here on the side, because Unit 3 takes up like 20% of the AP test. So here are the topics. You've already talked about intermolecular forces, states of matter. So today's video is going to be on types of solids, notes 14, and also homework 14. So there we go. We'll pull those out. You'll notice that in this unit, it's got states of matter is 13, and then 14 is solids, 15 is gases. We don't actually deal with liquids like at all, but we do deal with solutions. And a solution and a liquid, they're different, right? Because a solution is aqueous, it's where we dissolve something into water, and a liquid is where we heat something up so much that it melts. We don't deal with liquids like ever, but we're basically doing each type of matter. We've got solids, gases, solutions, and then chromatography is a technique that is specific to separating solutions. So that's kind of the organization. All right, so a couple of things. You'll want to pull out notes 14 and also homework 14. And somewhere in the packet as well, in that same section, is a paper that looks like this. It doesn't have a title. It's just a chart that has different pictures on it. So it's just randomly somewhere in the middle. So you'll want these 3 papers for today. I'll be kind of jumping back and forth. I got my new markers. And I feel like I could get like a sponsorship for my channel. Be like, today we're using, oh, sorry, the glare. Today we're using the Papermate Flare Medium. And like, I just love this pen because it gets me lots of money for my YouTube channel. Woo! Just kidding. That would be nice though, if I could somehow get like sponsorships so that we have more money for our classroom. I'd buy you so many nice things. All right, notes set 14, types of solids. And here at the top, I just drew in really big black letters, solids. I know it's written, but trust me, at the end of the year, when you're trying to study for the AP test and you're looking through that whole binder, it's gonna be real helpful when you've got some just real, real solid labels on it. See what I did there? Jokes. Okay, so solids are things that are very stuck together, right? Like we know that solids have particles that are very compact. There's 2 ways that particles can be held together. Either IMFs, intermolecular forces, or chemical bonds will hold stuff, aka particles, together. So if it's based on IMFs, IMFs are compared to bonds like a lot weaker. Remember, this is what we were talking about between Red Rover, and it's the difference between holding hands. That's like an IMF. It's pretty easy to overpower it. But a chemical bond is like how your arm is attached to you, and that's way more energy to get that to separate. So IMFs, these solids will not be as strongly held together. If your solid is being held together by bonds, those will be very strongly held together. We can determine how strongly something is held together by how much heat we have to put in order to overcome it. So the IMFs and bonds are like, stay together, stay together, stay together. And we're going to crank up the heat like warmer, 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 and see at what point does this substance begin to melt or boil. Those phase changes are indicative of how strong it was together. There are 4 types of crystalline solids. I'm skipping the visual appearance for a moment. There are 4 types of solids that I want to label here. So number one, make this real dark. I kind of just wish I had a fat marker, but I didn't bring any fat markers home with me, so I have to like shade it in. Number 1, number 2, go through and I'll pause the video so you don't have to watch me draw these. But 1, 2, 3, and 4. 1, 2, 3, 4. And it's a good thing that my paper doesn't have a backside, because like would have totally bled through. So the first one here, ionic solids. Ionic solids are very, 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 very strong, because their interactions, what's holding them together, are fully charged ions. So cations, anions, when you gain or lose electrons, you get that full charge. Zooming in. And looking at the picture, full positive, full negative, full positive, positive, negative. Notice they lined up in like a checkerboard pattern. This is our ionic lattice, is what they usually call it. Lattice just means checkerboard. So we have this ionic checkerboard, and it's very strong because opposites attract. In terms of charge. That's what Coulomb's law says. Opposite charges attract. A Coulomb is a charge, opposite charges attract. So this is very well held together. Due to the strong interactions between fully charged ions, ionic solids have low vapor pressures, okay, high melting points. That makes sense. You have to put in so much energy to get this to come apart. So we're going to have to put in a high amount of heat to get it to melt or boil, but probably just working on melting first. They tend to, let me zoom out, crunchy noises. They tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer. So if we're looking at my little lattice grid here, negative, positive, checkerboard, checkerboard, checkerboard. What happens if I were to just push like this top row, if I was like push with my finger and everything slid over one, so that you had 2 positives that would have been on top of each other, 2 positives or 2 negatives on top of each other. If opposites attract, then having positive on positive, negative on negative, positive on positive, that is going to repel away from each other so fast. So that's what it means by brittle. If the layer gets shifted, it just breaks. It's brittle. And that's why. So they tend to be brittle due to the repulsion of similar charges, like 2 positives, 2 negatives, caused when one layer slides across another layer. So there you go. They conduct electricity only when the ions are mobile. Okay. So an ionic solid, an example of this over here, we've got NaCl. You can see here's all the Cl minuses, chloride anions. I'll use a different color for the sodium, 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 so you can see. Checkerboard pattern, Na plus Cl minus came together to be NaCl. This is an ionic solid. It came from ions. Table salt, if you were to try and run electricity through it, that's not going to work very good. Like just salt from the kitchen table. And that's what this is saying. It's not going to conduct electricity unless the ions are mobile and able to move around. So table salt on its own, sitting on the table as a solid, it's not going to conduct electricity. But if we melted it, or if we dissolved it in water and the ions could move around, then it would conduct electricity. But it's not really going to conduct electricity in its current state. Okay, so there's the first type of our solids. 4 types of crystalline solids. Crystalline is the part that I skipped a minute ago. This is just referring to how things are arranged. You can have crystalline solids or amorphous solids. Don't get too caught up on these. We don't really study amorphous. I mean, like, I guess I wouldn't really worry about it. But crystalline just means that there's a regular repeating arrangement, like it has some sort of a pattern to it. So there's crystalline, where doop, 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 like it's very repeating, predictable. This is what we study in AP. Amorphous is not really what we study in AP. So ionic solids definitely fits into the crystalline solids because it's got that pattern of a checkerboard. Excuse me, of a checkerboard. That's usually how I recognize them. So going to the paper here, that just is a standalone paper. Here are some examples of ionic solids. Iron 2 sulfide comes from the iron 2 plus. The sulfur had a 2 minus, 1 of each. So it comes together kind of in this checkerboard pattern. Calcium is in the 2 plus column. Bromine is in the 1 minus, so we're going to need twice as many of him. Notice that that's present in the picture here. We have twice as many bromines for every calcium, but it's still kind of following like a modified checker pattern. And the one from up here, sodium chloride, 1-to-1 ratio. It's your ionic lattice / checkerboard. So that's usually the easiest. Like, notice that none of the other ones have that. Like Down here, not a checkerboard, similar, but not a checkerboard because checkerboards have like black and white repeating. So that's going to be your easiest way if you have to identify it from a picture. Okay. The next one is the one that I just was looking at on the bottom here that I said was similar. These are metallic solids. Metallic solids are when you just take metal and you're looking at just metal. Ionic solids, this is where you're taking a metal that's formed a cation, and we're mixing it together with a non-metal that has formed an anion. And we're putting those opposite charges together. With metallic bonding down below, we're just putting multiple metals together. So really quickly here, I'm going to do a screen share, just a reminder of what constitutes as our metals versus nonmetals. So most of the periodic table is metals, that blue region that you're looking at here. And then the other one, the yellow up top, that is the non-metals. So there's just your reminder. So going back then to this image, platinum metal, just pure platinum, means every single one of these, platinum, 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 platinum. Not a checkerboard because it's the same thing over and over and over and over. Nickel, same thing over here. Nickel, 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 nickel. Great. Now, before we even talk about the middle one, how are metals staying together? Because I thought that metals lost electrons to become positive. So how are we putting positive next to positive next to positive? Isn't that supposed to like not work, right? So here's how this one actually comes together. It's really cool. Okay, so I'll screen share and let me switch it back to my face. Hello. Metals lose electrons. That's what they do. When they lose electrons, they become positively charged. So far, this with all the plus, 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 that's what we're looking at. That doesn't look at all stable. And it's not, it wouldn't be in that particular arrangement. But what's happening, let's play the video. There's no sound. Well, there is, but I turned it off. So the, go back. So what it's showing us here is that we have the positive cations, but those electrons that were lost, they didn't actually like go anywhere. They popped off of the metal, but they're still present. If there's no non-metal to accept them and steal them away, then all the metal can do is go, don't want them, don't want them. But if nothing is taking them, they just sit there. And that's what's happening. We have positive ions in what they call a sea of electrons. The electrons are just sitting there because nothing's grabbing them. No non-metals, like electronegative, nothing's grabbing them. They're just sitting. Which is important because the fact that they're still sitting there helps stabilize all of these positive charges, because it's not actually two positive charges together anymore. It's a positive charge with like some electron jello around it to kind of stabilize it. So here we zoom in and it's showing there's that positive one in the middle, and there's the electrons that are like helping to stabilize it. So that's kind of cool. Let's see. Skippy, skippy, skippy. Skippy, skippy, skippy. Skippy, skippy. Okay, now this is what we were talking about before. If you take a metal, the one, if you take an ionic compound, the one from up here, the checkerboard, look what happens to the checkerboard when we smash, oh, see how it was brittle and it just broke? Checkerboard breaks. And then it does like a cool thing here where it shows why. When that hammer came in and slid one layer down, it put positive next to positive, negative next to negative. And then the atom was like, oh, wow, that totally sucks. Bye. Spreads apart. But here's the cool thing about the one we're studying right now. Metallic solids, we've got sea of electrons. See how the hammer just comes in? I love this part. It's literally my favorite part. When the hammer comes in and it's able to like smoosh, smoosh, smoosh. One more time. I love it so much. Smoosh, smoosh, smoosh. Because the electrons that are in there are like jello stabilizing everything. So that's why metals are malleable. That's why you can take a paper clip and bend it. Malleable means bendy. I think, is there anything else in this video I wanted to show? Not really. Why are metals good conductors? We will talk about that though. I don't know if we'll be able to show that. Okay, so realistically, it's not just positive, positive, positive. We have a sea of electrons model that's keeping this together. So it's showing you, this is the, let me get a new color. I should like really keep all my colors straight, but I just love my new markers so much. There's the positive cation core. Here's another one. But they're being stabilized. The positive cores are being stabilized by these electron, 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 electron that had fallen off. If you are a group 1 metal, meaning you're in the first column of the periodic table, stuff like Na plus or lithium plus, you are losing 1 electron. So if I went through and counted, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 positives, and 1, 2, 3, 4, 5, 6, 7, 8, 9 corresponding electrons. That makes sense. In a group 2 metal, something like magnesium 2 plus, or what's another one? Calcium 2 plus, they're losing 2 electrons. So for every positive core we have, we've got more electrons corresponding to each, more sea of electrons. All right, so metallic bonding is based on a sea of electrons model. I'm going to write that really big, even though it's already written, just so that it's easier to find later on if you ever want it. Metals are good conductors of electricity because of the free electrons. Have you ever noticed electricity? Interesting. Electricity is the movement of electrons. Wow. So back up here, these guys could not conduct electricity very well unless their ions or charges were mobile. That totally makes sense because you're not going to have electricity unless your electrons or charge is moving around. We have lots of charge moving around. Look at that sea of electrons. So of course, these are going to conduct electricity really well. You already knew that. You already know metals conduct electricity. Conductors of electricity. Free electrons. Metals tend to be malleable, bendy, because we were able to kind of smoosh this around. We saw that in the video. Due to the ease which the metal cores can rearrange their structure. If you have platinum on platinum on platinum on platinum, you have a sample of pure platinum metal. Nickel on nickel on nickel on nickel, pure sample of nickel. When you start mixing together multiple things, like here we have copper, Zn is zinc. Copper and zinc together, blending those metals makes brass. Brass is not an element. When you go through the song and you're like, there's hydrogen and helium and lithium, beryllium, blah, 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 blah. You're never going to find brass. Brass is not an element. Brass is the combination of copper and zinc, which are on the periodic table. Copper, zinc, and gallium, uranium, and arsenic, or whatever. So when you put this element and this element together, you get brass. Brass is what we call an alloy. An alloy is when you have two different metals that have come together like that. It's important to note that alloys are always stronger than the individual metals. So if I had pure copper, copper on copper on copper, zinc, 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 zinc on zinc on zinc, separate, they would each not be as strong as putting them together to make brass. But like, why? Now here's what's kind of cool. I like this story a lot. Let's hold on one second. Pause. So just doing a quick Google search here. Examples of alloys. Screen share so you can see. Pull out your phone if you want. It's actually kind of cool. So here are some examples. Let's see. Whoa, let's put my face there. Here are some examples of alloys. So bronze is where you take copper and tin in the ratios that are shown up there. So if you take anywhere from like 78% copper to 95% copper and 5% to 22% on the tin, take those two metals, melt them together, you've got bronze. Cast iron, sterling silver is the one that you've probably heard of. That's where it's like 93% silver, but it has a little bit of copper in it. Question is, wait, what? Why? Remember that they're stronger when they're together. We haven't talked about why, but that's the rationale why you might want your jewelry to be a blend. Pure gold, if you had a gold ring, that would be really, really bad because pure gold is like super squishy. So we have to take 75% gold, 13% copper, 13% silver, put it all together. So that way, when you try and smoosh your jewelry, it doesn't just smoosh like butter. And then brass is the other one that we talked about, where you take copper and zinc and put them together. When I'm back in the classroom, remind me, especially at the end of the year after the AP test, there is a really, really fun, a really fun lab that you can do with a penny. Pennies have zinc on the inside and copper on the outside, the new ones, because copper is more expensive. So why make an entire copper penny when we can just put like cheap zinc in the middle, copper on top, and no one will know the difference. But what's cool is if you've got copper and zinc, if you were to take the penny, heat it up in like a Bunsen burner, then you could put them together and you could get a brass penny. Pennies aren't supposed to necessarily be brass, but we can make them brass in the lab. If you're wondering what that penny would look like, here I just pulled up, it's not the best image ever, but normal pennies kind of have this look to them, like a rose gold. If we decide just to put, we can put more zinc on top of the penny. It'll stick real good and you can get a silver looking penny. And then if we melt them together, the zinc inside, copper on the outside, you can get this gold looking one. Okay, and it took me a minute here. Not that you guys know, but it took me a minute here to find, here's an actual photograph of the different pennies. So on the right, this is just the regular penny. It might even be a penny that is pure copper. Like I'd have to look at the date and see what the date is on that, because they switched from full copper to copper zinc after a certain year, and I don't know when that is. But anyway, copper on the outside of this one. And then if you take the copper and the zinc inside and fuse it together through metallic bonding, you can get the one on the left, which is the brass alloy. And then this one here is just showing zinc on the outside, copper on the outside, fusing to make the alloy brass. So remind me when I'm back. The sub can't necessarily do any labs with you, sorry. But that is definitely one that we can do. And I'm super open to doing stuff like that all the time, every day, once my baby's born and it's a little bit safer, but also once the AP test is over, because we will have all the time in the world. Okay, so back to this. Copper and zinc, fuse them together, you can make a brass penny. The reason that alloys are stronger than the individual metals is because thinking about like putting copper and zinc together to make brass, copper and zinc are not the same sizes. They're pretty similar, but they're not exactly the same size. So if you were to fuse them together, let me try and draw my best picture for you here. if you've got two different sizes of atoms, let's try and do this. You can't push on one and slide it over. With ionic solids, we could for sure do that, and it was a problem. We like push, and it slid the whole plane slid, and it broke off, was really brittle. But look, when we have the different sizes, that makes it so the layers don't slip. So different sizes in alloys mean the layers don't slide. If the layers aren't sliding, then you're good. You've got like a stronger piece. So what's really interesting is how steel was invented. And at the time, during like, you've heard of like the Stone Age or the Bronze Age or whatever, back when weapons were still being made out of iron, just iron is not on its own super strong. It's bendy. So they had iron weapons. That's cool. Like you get stabbed with an iron sword, like ow, but kind of bendy. So here's what they thought. They thought, we're going into battle and we need some extra strength. So what we're going to do is we're going to take these bones from the animal, like maybe they killed a wolf, or maybe they found a bison carcass, and they would take those bones and they put them in the fire, because fire was just like so cool back then. It's still cool. But they would like put them in the fire, and they thought that by doing that, the spirit of the animal would like come out. So they're like, okay, wolf bones, put them in the fire, on fire, and let's put our weapons into the fire and like whack them, because wouldn't that mean that the spirit of the wolf is now in my sword? Logic, not so great logic, but that's okay. And what was crazy pants is then the next day when they pulled their weapons out because they needed to cool and stuff, holy crap, their weapons were so much better, like legitimately actually better, not just thinking it was better, legitimately better. And they were like, whoa, my sword has the power of the wolf in it. Ow. Like, and they kept doing this. But the science behind it is that the carbon in the animal bones, which has some metallic, it's semi-metal, it's got some metallic properties, and the iron were alloying together to make steel. Steel is like the strongest freaking thing ever. Like we use steel in modern day buildings. So these like ancient people thought their weapons were getting strong because of the wolf spirit, but in reality, they actually made steel. So I'm not saying they were wrong. The wolf did help, but not quite in the way that they were saying. So there you go. That's how steel was invented. For sure, metallic solids are like one of my favorites. The one underneath it now, we're looking at network covalent solids. And the way that you're going to distinguish this one, looking at the paper here, I just like this paper because it has lots of comparisons on it. What you're looking for specifically in a network covalent solid, covalent is a type of bond. You are looking for things that are bonded together in some sort of a net or a network. So diamond is made of, I should really pick a different color for each of these, but I forget. And then I use the same color, and then it gets probably not confusing at all for you guys because you just use pencil. But carbon, 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 bonded, 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 but also bonded this way, bonded this way, bonded this way, bonded, 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 bonded. Look at like how much this net or network extends. That's what distinguishes this. These are actual bonds. So obviously this is a very strong structure. Bonds are like ripping off someone's arm. That's not going to happen very easily. And you've got that happening over and over and over and over and over again. So network covalent solids are very strong, which you already know, diamond is like one of the strongest things in the world. So some other examples here. Silica is made of a silicone with some oxygens. Again, bond, 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 bond. Network covalent. Silicone can just bond with itself. Bond, 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 make a net. It pretty much extends just forever. And that's network covalent solids. If you're looking up here wondering like, well, wait, this kind of looks like a net. Why don't these ones work? And the distinction is if you zoom in, crunchy noises. Okay, look at the picture, because sure, we do have some things that are bonded. It's N2, the nitrogen is bonded to the other nitrogen. It's a triple bond. It's got some lone pairs in case you're wondering. But nitrogen, nitrogen, bonded, 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 bonded. But they're not like bonded to each other. And that's the difference. This was bonded like in every direction. This is bonded together, and the interactions between them here, here, all of these yellow ones that I'm putting in, the dashed ones, those are IMFs. IMFs are holding the pieces together in a molecular solid. In a network covalent solid, the actual bonds are holding it together. So ice, H2O, sure, the water molecule is bonded to itself, but there's an intermolecular force. There's an intermolecular force. I think that's one, that's one, that's one. The water molecules are like separate entities with IMFs between them. Same thing with dry ice, but this one's a little bit easier to see. There's a dry ice. There's a dry ice. Bond, 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 bond. But no bonds are actually connecting the dry ices. We have IMFs. That makes sense? Network covalent solids, back in the notes then. There's kind of two ways that this happens. Here's diamond again, and it's just carbons. Carbon, 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 bond, 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 bond. Bond, 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 and everything's bonded together. This is what we call a 3D network. It just expands in all directions. Graphite, what's in your pencil, is also made of carbon. But why on God's green earth is diamond really, really, really hard, and graphite is really, really soft. So soft that you can use it in pencil lead. Well, the difference is that this one has bonded in all 3 directions. Graphite is still network covalent, bond, 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 and making a little net here. Net, net, net. See the net? But because it's 2-dimensional, it has IMFs between other layers. Here's another layer. Layer 1, layer 2. This is network covalent. The whole thing is network covalent, but the layers are kind of stuck together through IMFs instead of bonds on bonds on bonds. Due to those strong covalent bonds, whether it's in a 3D arrangement or a 2D arrangement, they're going to have high melting points. Molecular solids, these ones are literally molecules, molecular molecules that are cold, and the IMFs can hold them together in a solid form. Molecular solids are composed of distinct individual units of covalently bonded molecules. Do you see the difference how this is a net and this is like one molecule? One molecule IMFing with another one, that's molecular. Nets, any type of net structure, network covalent. Let's see. They're attracted through IMFs only, which are relatively weak. Subsequently, you're going to have low melting points. It does not take very much energy to melt this type of solid, because you're just overcoming the IMFs there. So there you go. You can read the rest if you want, but I'm not super concerned with this one. So those are the 4 types of crystalline solids.